Hello, everybody. Thank you for coming. So today we're going to talk about mainframes. And this subject I really am passionate and excited about because, well, I get to pop shells on machines that look a little bit like this. And, fridge-like machines, true, but, cool blue neons. I mean, what's not to love, right? And, I know what you're thinking. Is that really what a mainframe looks like? I think you're probably more used to pictures that look a little bit like this or that, like big old gray boxes, giant red tapes that nobody cares about, that some people even call legacy. Well, it's true, that's what they used to look like, but in the 1960s, I mean, they have evolved since like every other product from the 1960s. Like when I talk about Tesla, for instance, when I say Tesla, you don't picture a Ford 1964 machine with great suspension brakes, right? You picture a freaking car that can park itself. Well, it's the same thing with the mainframe. They have evolved, and they're very beautiful piece of hardware that actually performs well, and they have amazing stability and amazing performance criteria. And anyway, just to show you basically the latest mainframe that was released in 2017, so you can hardly call it legacy. Now I just put the specs that you would look into a computer if you're looking at it on Amazon, but just to give you an idea. So this is the IBM Z series mainframe, and we're only going to talk about IBM Z series in this talk. So these are just a few of the specs. So you can see 32 terabytes of RAM, 170 processors, clocking at 5.2 gigahertz. This is not a machine that you use to run your email server. This is a machine that you use or you want to spend money on to host your most sensitive business applications. Like my friend Chad says, if it's critical, it's running on a mainframe, no questions asked. And these machines have amazing stability, have amazing performance that you cannot find or easily find anywhere else, basically. Oh, and by the way, I just included a link for the presentation because there's going to be some demos, etc. So if you can't see it quite well, just download it. I'm going to keep the link here. So who needs these machines? Who needs such performance, such reliability? Well, I want you to think about every basically critical service that you rely on in your everyday life. Let's say wire transfer, money, getting money out of an ATM, booking flights to come see conferences, hotel booking. All of these important transactions occur on a mainframe. 87% of credit card transactions go through one of these machines. So, it's just wrong and sad to call them legacy. These machines power the world economy, and yet we do not, as pen testers and hackers or whatever, we do not give a shit about them. And that's just too sad. And so just to give you an idea of some of the companies that actually rely on a mainframe, so I put a slide and I put a lot of logos of the company, but I couldn't fit them all in. But I hope you recognize some of the companies that you care about, that you use in your daily life. Some of them maybe are your clients, maybe it's your bank, maybe it's your airline. And if you do not find the company that you care about on this slide, maybe you'll find it on this one. My point is, a lot of companies use these machines, yet we as pen testers, we prefer going after domain admins or after email servers. I mean, honestly, I do not care about the emails, about the CEO's email if I can add a 0 to my bank account. And guess where the bank account is stored? On a database, on a mainframe. So there was this awesome quote by Dominic White that said, pen testers tend to resemble other pen testers instead of resembling actual attackers. And it's so true in the world of the mainframe, at least, actually. So before we move on, just a little bit about me. Pen tester at PwC France. I'm mainly hacking Windows and Unix stuff, right? I'm as guilty as the rest of you. But I first got my hands on a mainframe in 2014. I was working at Wavestone at the time, and we were doing this, global audit, basically scanning everything that had an IP address. And we found this basically telnet-like service. And you Google it, you find the word mainframe, etc. And we were so excited. This is an old machine that's sitting on the network. We're so gonna pull the shit out of it, but we didn't for various reasons, like lack of tools, lack of easily accessible documentation, lack of talks about it. There was one talk at Black Hat at the time, and so I decided to look into it, do the research, develop some tools. I presented some of my tools last year at Hack in the Box, and so this is basically the continuity of that talk. And all of the tools that I will present are on GitHub, my GitHub, so you can go fetch them. And here's my Twitter if you want to follow me. Promise I don't only talk about mainframes. So what are we going to talk about today? The meat of this talk will be about post-exploit stuff, what do you do once you have a shell on a mainframe. However, I found out that people actually struggle a little bit with the idea of like executing code remotely on a mainframe. Like they have trouble believing it. Like I had to convince some actually pen testers, clients or whatever that, hey, it's possible to attack this machine like you would any other machine. So I'm just, before going to the fun stuff of like assembly, playing with memory and all that cool stuff, I just want to do a quick recap of like the current tools and current techniques to execute code on a mainframe. Like how would you approach this machine if you find it on a network? So just 10 minutes briefly on that, and then we'll go and do some really cool stuff, okay? Brilliant. Now, this machine, if you find it on a network, you want to communicate with it, it has an IP address. You can find like HTTP, FTP, SSH, all the cool, normal, classic stuff, because it basically has a Unix on it. So yeah, again, I'm only talking about IBM Z series. So the main protocol to communicate with this machine is called TN3270. Now, TN3270 is nothing but a telnet. It's a rebranded telnet, that's it. Except that you will need a virtual emulator, or the real one, the real terminal, to basically download it and communicate with the machine. And it's just telnet with additional data streams, etc. So there's X3270, there's WC3270, there are other tools. You just download them, and then you can communicate with the mainframe. But the thing is, like telnet, TN3270 is clear text. So right there, you have a possibility of sniffing the network and just get credentials. And so many clients like spend like minutes, hours arguing that their machine is unhackable, so we should not apply this or that security measure. And then like this one question, like, okay, do you run TN3270? Yes. Is it over SSL? No. And they're like, well, what the hell are you talking about? It's unbreakable. Anyway. So just to show you basically that it's possible to, like, there are tools, like if you download the latest EtcherCap on GitHub, you can just basically get a TN3270 dissector that will, parse the network, and I will just show you like a basic man-in-the-middle attack with RP poison. It actually works. So here we launched EtcherCap, and you can see that RP poisoning mode, like classic 1990s stuff, right? And then on the other side, we launch an emulator, mainframe emulator. You can see we type in the IP address. It connects to port 23. And here we have the welcoming screen on a mainframe. So this is custom designed. I designed it. It doesn't look as cool as that normally. So you have a choice between two apps, TSO and Euro. So TSO is just the bin bash. It just executes, it lets you execute commands. So we type in TSO, and then we can type in our username and password. So this is what an actual connection on a mainframe looks like. We type in our username, password, and here we have the prompt where we can execute commands like netstat, like ping, like nslookup, like normal commands to list files, etc. And you can see here that the EtcherCap basically just got the username and password, just to say that, hey, simple attacks like network sniffing still work because nobody cares about implementing SSL on a mainframe. Like Soldier of Fortran, the same guy that wrote this EtcherCap dissector, scanned all the mainframes on the internet. Only half of them use SSL. So you can imagine this state in how it is in the internal network where nobody cares about SSL. And even if SSL is present, the virtual emulator that we just used is not as modern as browsers. It doesn't maintain a list of certificates that it needs to check, etc. It doesn't have that. So even then with SSL, you can actually perform SSL interception and SSL decryption. So just to say that I don't need a 0-day to go inside a mainframe if I can sniff network and get credentials. So just staying in the very simple attacks that actually work in the field, we're going to look at brute force. Like something that you would not think of trying on a normal environment, or like you would do in a last thing that you would do in a Windows environment. But it got me into so many mainframes, it's insane. It works. And I'm going to show you very quickly how basically I go about it. It's just like the TSO, like the command line interpreter that lets you connect to the mainframe and authenticate and execute commands. It tells you if the username is valid or not. Now I chose a poor example, but usually there are some restrictions on the username that makes them very predictable. So the username cannot exceed 7 characters. It's always uppercase. It has 3 special characters. You can input only 3 types of special characters, called national characters. And you cannot start it with a number. So all these restrictions makes it like, the companies cannot get too creative with their usernames. So all the developers would be like dev001, dev002, or users from a certain department will be like, for instance, GA0 and then 3 letters and something like that. So all of this makes it very easy and very practical to actually conduct a brute force attack to enumerate users. And it has worked so many times. And there's an Nmap script to do it. Again, courtesy of Soldier of Fortran. So it's included in the latest Nmap, so you do not have to do anything. Just think about this type of attack when you're facing a mainframe. Now, once you identify the list of usernames that are valid, obviously the next step is to guess the password. Now, the password that I usually try and with which the one that gives me the most results is just passwords equal username. It's so stupid. But it works. It's like I said before, like you don't need 0 days if these simple attacks still work on a mainframe. I mean, come on. And so just to show you how effective it is, I'm just going to show you a dump that like basically I did on a client assignment. Like a dump between, like we dumped the entities.did file, like the Active Directory hash table on Windows, and did the same on the mainframe. So 1,000 users on Windows, 998 users on mainframe. And so you can see that on the Windows world, in the Windows world, only 5% of the accounts like used password. The password was username plus a number. On a mainframe, 27%, where the password was equal to username plus a number. 19% password equals username. Now, obviously, this is a totally biased result. But what I want to convey is that there's a really difference or a gap in security maturity between the Windows world and the mainframe world. Like in the Windows world, it has been broken so many times that people have no trouble believing that it's attackers are out there and they're after the platform, they know how to exploit it. The mainframe world is the only environment where I actually heard the following justifications. We don't need to worry about that. Hackers will not go through the trouble of actually doing this stuff on a mainframe or learning the mainframe or developing tools to pen test it or something. They don't know how to do it. It's closed. That's like, it's insane to have this kind of justifications in 2017, given the multiple security contacts that are out there. But it's still true in the mainframe world, so people just don't care about it or don't care about securing it. So these attacks work. So that's basically the whole point behind this small statistics. Now, these are 2 attacks that work. There's another one that I basically showed last year, Hack in the Box and Hack in Paris. I'm just gonna very briefly describe it. But if you want more information about it, just go see the talk because it's a bit heavier than that. But I'm just gonna graze over it very quickly. Now, if we come back to the main welcome interface of a mainframe. So we had the choice between, TSO, the command line interpreter, where we can execute commands, and Euro. Now, Euro is just a business app that's present on this mainframe. So think of it like when you go to your bank and your banking operator, like for instance, wants to get customer information about your account or whatever like that, they may use in-house developed app, right, over TN3270. And it looks a little bit like this. So if you type in Euro here, you get this authentication form, and like the banking operator authenticates itself, and then they type in like your customer number to get information or to make a wire transfer or whatever. But the thing is, this is no web, obviously. And what I found out is that almost all interactive applications that run on a mainframe run over TN3270 that are heavily used by on the mainframe world. They run over same middleware, or most of them run over the same middleware that's called CICS, Customer Information Control System. Now, CICS, there are hundreds of books about CICS, even more maybe, but I'm just going to try to summarize it in one sentence, and I hope I'm not going to offend too many mainframe purists. But to me, CICS is really a combination of an Apache Tomcat and a CMS like Drupal. In a sense that a developer will code his app in COBOL, assembly, C, or whatever, compile it, and then put it on CICS, and CICS will make it available to everyone. And all the requests that come in will get routed to the proper sub-application or sub-task. CICS will do like the memory handling, task scheduling, caching of files, handling locks and resources on disk, etc. So it really is a middleware, except that it was developed in 1968, long before the web, long before, before even the internet. So basically, and why is it still used? It's just because it can handle 20 billion transactions a day, simple as that. So it's very powerful. But the thing is, just like on Apache Tomcat, where one of the checks is to find the /manager/HTML to upload a web shell, well, the same thing or the same concept applies to Kix in the sense that the idea is to find a combination of keys. There's no notion of an URL. So the idea is to find a combination of keys to press to exit the app. And when we exit the app that's available, Kix asks us, well, where do you want to go? Which other app do you want to launch? And there, the idea is to launch an admin app that will allow us to execute code. Now I'm just briefly summarizing what it is, but just to show you what it looks like, so it's maybe clearer. So here we have euro, we type in euro, and here we have the app. So instead of authenticating the app, we just click on PF3 on the top right corner. And we click on PF3, we have a blank screen. And now here, basically, Kix is asking us where you want to go, and we type in the admin utility, and if it's not protected, we get access to all these cool functions that may seem obscure, but one of these functions lets us read and write files. And I'm not talking about configuration files. I'm talking about business files that contain customer data, that contain balance, that contain all that cool stuff. So I wrote a tool that will basically take advantage of all this stuff, and it will automate all these steps that I showed you and some more. And it will find the right combination of keys to exit the app. It will upload a reverse shell, coded in JCL and Rex, like some special scripting languages on a mainframe. And it will give you a reverse shell, just like classic old reverse shell. And so this is the tool that I presented earlier. It's on my GitHub if you want. I'm just going to show you. So this is remotely, basically sitting in a listener and then remotely talking with the mainframe with this tool that's called Kickspoon. And like I said, it will alleviate some or bypass some protections if there are any. So, it does all the stuff. I'll let you check it out later. But this is just to show you an actual case of a reverse shell on a mainframe that, hey, it's possible. So you can see here it did all its magic. And then here we have a TSO shell prompt that basically lists user. We can type in commands, netstat, list files, and all that stuff. So all these small tips are just current ways of executing code in a mainframe. But there are many more. You can execute code through FTP. It's a feature, it's not a vuln. You have network job entry. There's buffer overflows on a mainframe. Just that, there are buffer overflows on a mainframe. And people still think this machine is unhackable. It's just like any other machine. That is one of the key messages of this presentation, and we should care about it. Because if, Windows goes down, nobody cares about it. If a mainframe goes down, citizens are impacted. So it's that critical. And check out these awesome guys' talks. They've developed tools and they've presented a lot. They've contributed a lot to the security to security on mainframe. So check it out. Anyway, so now that we are comfortable with the hypothesis of having a shell on a mainframe, I hope, what can we do once we are on the machine? We are a standard user. What's blocking us from going root and doing whatever we want? What does it even mean to be root on a mainframe? Now, I'm only going to talk on ZOS, about ZOS, which is the most common operating system on a mainframe. And so once you have a shell on IBM Z mainframe hosting ZOS, the main hurdle between you and accessing everything, the main obstacle, is called most of the time RACF. Now, RACF, Resource Access Control Facility, is a product, one of 3 that you may find on a mainframe. Think of it like PAM, right? It does authentication, but it also does access control, and it's mandatory access control. So think of it like a big giant firewall table that says this user can access this resource, this particular time of the day, with this type of access, read, write, update, whatever, from this terminal. And so on a firewall, you would have 1,000 rules, RACF, 50, 60,000 rules easily. So it's mandatory access control, yeah? And just one small digression. For people that think that a mainframe is secured by default or by design, no such thing. When you get a mainframe, when you get it from the shop, RACF is not activated. So let me just, let that sink in. You do not have access control enforced when you get your mainframe set up. In fact, one of the checks in any auditing guide is to actually verify that RACF is properly enforced in control, in fail mode. So by default, if you access something, RACF will tell you. It will raise a security notice, but it will let you access that resource. So just one of the checks is to activate this protection. So think about it. Next time somebody says, oh yeah, our mainframe is locked down, like IBM did a good job, and they did a good job. This is a highly customizable machine. You cannot expect it to be secured by default. It's not a freaking iPhone. It's, it's a machine that you need to tune, and not only tune performance-wise, but also security-wise. So that's small digression right there. So anyway, on RACF, you have, standard users, and the equivalent of root, I would say, on a mainframe would be special. Now, special does not mean that you can access anything. It means you can give yourself access to anything. So again, mandatory access control. You need to write a rule that says, hey, I can access that resource, even when you're special. There's another attribute that's called operations, which means you can access any resource unless there is a rule in RACF that says, hey, you cannot do that. So it's still a very interesting one. And auditor means you can manage some auditing classes and do some fun stuff with login classes. We're not going to really care about it that much. Anyway, so when you type in the list, so if you go back to our TSO command prompt, if you type in the list user command, you will basically see your attributes. So list user or LU, like we typed before, you get to see your attributes. So in this case, we're special. You can see here we're special with operations and even with auditors. But what if we have 0 privileges? How can we become root, right? And that's where we will play with ZOS internals and play with some memory and do some cool stuff. Now, just before we move on, because we're going to talk a little bit about assembly and some low-level stuff, I just want to stress out that Z architecture it has nothing to do with Intel, okay? It's proprietary CPU. It has its own instructions, like over 1,100 instructions. So it's not ARM, it's not x86. It's it's another CPU basically. So you have many variants. Each instruction has many variants: memory to memory, register to register, immediate, whatever. On x86 we have 8 general purpose registers. On Z we have 16 general purpose registers. But the main one, plus dozens others, control registers, access registers, floating registers. But the main one that we're going to focus on is called the PSW register. Now, the PSW register is like the EIP register in x86. It holds the instruction, the address of the next instruction to be executed. But it also holds some other important control flags. Like this is the register that will say if we're in user mode or kernel mode, let's say, for instance. So we're going to focus on it a little bit when we inspect, when we debug our programs, etc. So, ZOS, like any modern operating system, and I stress the word modern, uses data structures or keeps data structures in memory to describe the current state of the operating system. So on Windows, you have eProcess structures that, describe the processes that are running. They're kept in a doubly linked list, etc., all that stuff. Same thing on ZOS, except that these data structures, they're called control blocks. So think of it just like, bunch of data with a bunch of pointers that describe the current state of the program. So tasks, user running, etc., etc., etc. And RACF initializes one of these control blocks that's called the ACEE, accessor control environment element. And basically what accessor element environment, oh my God, I'm going to make it. No, I give in. Anyway, check it out. These acronyms are impossible. So RACF basically initializes the ACE control block, and it stores the user ID, the group, and the privileges of the current user. Like think of it as the token descriptor or the security token descriptor on Windows. So this control block holds the current privileges of the user. And when you type in list user, or if you want to check in, like you go through memory and find this control block, you always want to start at virtual address space 0. If you want to find actually any control block in memory, you start at virtual address space 0. That's where you find basically the PSA or the prefix saved area, the genesis control block, I'm going to call it, but just like, the main one that references all the other major control blocks. And you can see here it's just a matter of walking from one pointer to another. So you can do it in assembly in C or whatever. And see, basically we just go to offset 548. We found a pointer to the control block that describes our current virtual address space. At offset 108, we find an extended pointer, an extended control block. And at offset 200, we go and we actually find a pointer towards the ACE. Now, All these offsets, or most of them I would say, are documented in MVS data areas, so PDF files. Like there are 4 or 5 that are released by IBM, each 5,000 pages long. But you find all this stuff inside. So you can have at it. I'm just going to leave it there, for future reference if you want to do the same thing. And but basically it's just walking from one pointer to another, right? So at offset 38 in this structure in memory, we have the user flags. So you can see here that this bit controls if we're special, operations, or auditor. So the idea, naively, I'm going to say, one that is not familiar with the platform and the protections in place, one of the possible vectors of attack is to write a code that will find this control block and update this byte. Again, like I said, it's naively. We are very naive. We just want to write a program in assembly that just finds the structure and patch it in memory, and boom, see if we can become root or special. So that's the first step of the attack, right? But if you go ahead and do that, you will get this beautiful error that says, hey, you can't, obviously. So there happened S0C4, which just means that we have a memory exception that occurred. Now what happened was that on ZOS, or on Z, sorry, it's a protection that you do not have on x86, but basically each page frame is allocated a protection key, 5-bit, that is composed of a storage bit on 4 bits and a fetch protection bit. So each 4K of memory has this protection, right? And let's just focus on the storage key. That's the main key. That's the main important piece of information. So there are 16 possible values, obviously. So if a patch of memory has a storage key between 0 and 7, it means that patch of memory is allocated by system services. If that patch of memory has a storage key of 8, it means it has been allocated by users. If that page frame has a storage key between 9 and 15, it means that patch of memory is real memory. There is no translation, virtual address space translation, none of that. It's real memory you're dealing with. So you have other problems like process isolation and all that kind of stuff. So anyway, when a program accesses a patch of memory, the current storage key in the PSW register gets compared with the storage key in memory. If they match, we have full access. If they don't match, then we get denied or we only get read access depending on this fetch protection bit. So if we go back to the error of our simple program that was running, you can see that the PSW at the time of the error, the storage key was 8. You can see here. And that means that the ACE, the control block, was probably in a space that, had a storage key different than 8. Actually, it's a storage key of 0. So here I just mapped all the possible outcomes. So if the PSW key you have is 0, you can access anything in memory. So full read, write. If it's not 0 and the storage keys match, full access. If they don't match but the fetch protection bit is on, it's none, no access. If the fetch protection bit is off, you only have read access. So the ACE falls in this category. So the storage key is 0, but there is no fetch protection bit. So we can read it, but we cannot update it. Right? So now the attack plot evolves, and now before patching the ACE in memory, where the privileges are held, we need to switch the storage key in the PSW register. Now there's an instruction to do it in assembly that's called the modset macro. However, this instruction, like all other powerful instructions, are only available in kernel mode, or what is called supervisor state. So on ZOS, basically, supervisor state equals the kernel mode on Intel. Problem state, it's user mode, right? So some instructions are only available in supervisor state. So the question now becomes, how do we get into supervisor state? Now on Linux, let's say, if you want to go into kernel mode, you just write your program, compile it as a loadable kernel, and then use insmod or modprob or whatever. On ZOS, it's very different. On ZOS, you have some kernel folders that are called APF libraries. And any program that is dropped in these folders can go into kernel mode, no questions asked. So let me stress that again. You have kernel folders like 60, 100, whatever. They can be custom defined. Most of them are. You have no way of easily listing them on a mainframe, except if you're running the ZOS 2.1, which introduced an instruction to a command to list APF libraries. But you have no way to easily, except from going through memory. That's what we're going to do, basically. And you have these folders, and if one of them is not protected, and in fact, many of them are not protected, like almost all, like not almost all the assignments, but a lot of the assignments that I had, actually, we found these APF libraries that were not protected, and the client went, well, who cares? Like, can you show me what it can do with it? And I'm like, well, that was like years ago. And I was like, well, theoretically, it is possible to code a program in assembly that will do blah, blah, blah. And he's like, yeah, shut up, go ahead. Like, I don't want to hear about it. And that's, people believe that this knowledge is so out of reach, but in fact, it's not. And, I'm going to show you later on the program that will explore all of this. We will see it's very trivial. Now, the idea is to find these APF libraries that are the one we can alter, and then, then we can move on with our scheme. Find an APF library with alter access, write a program, drop a program that will switch the PSW key, and then having the supervisor state, having the PSW storage key set to 0, we can patch the ACE bit in memory. Now, to find APF libraries, like I said, if you're running ZOS 2.1, there's a simple command to do it, CSV APF. But if you run in like other versions, you have to go through memory. And to find them, now I'm not going to detail the scheme, but it's just basically just going from one pointer to another. It's as easy as that. So I'm just going to leave it there for reference. But I wrote a tool that will do all of this automatically, so you do not have to worry about it. But I'll just leave it to be exhaustive. And once we found all the APF libraries, we just check which access we have on them. And the program that we're going to drop inside one of these folders it looks a little bit like this. Now, I do not expect everyone to know like Z architecture assembly, but I just want to go very quickly through the program to show you that it's not magical, that it's not too complicated, that it's not really actually complicated. So we have the first section that says, hey, our program runs in 31-bit, right? We have the program prologue where we save some registers, and then we say our stack register will be register number 12, because there is no set or defined stack register. You have to define it every time. And then we call the modset macro. We switch the keys to 0. We go to supervisor state. And then it's just a matter of loading different offsets into register until we find the ACE, right? And then we just execute an immediate OR to flip the proper bytes at offset 26 and 27. So that's it, basically. This is the program that will make us root on a mainframe. We just need to find an API library where we drop it so it can run into kernel mode. That's it, basically. So just to show you how simple it is. Now, however, compiling this piece of code took me nearly 2 days to figure it out, honest to God. It's not a simple instruction. It's not one instruction to run on a mainframe to compile code. It's a freaking script that you have to write. So I decided to wrap this program in a scripting Python-like on a mainframe. It's called Rex. So it will properly compile the code, link it with the proper options so it can put it inside an APF library. It will find the APF library with alter access, and we'll drop it automatically so you have just one command to execute. But when I first run this program, it worked, but it was tricky actually, because when the program runs, it runs in its own virtual address space. So when it finds the memory to patch, it patches its own virtual address space. So true, the program became special and then quit. But my user was still standard user. So there's this separation, virtual address separation. So I had to add this small instruction at the end that says to the program, hey, when you're special, well, add a rackf rule that says that user, me, is also special. Hence this small instruction at the end, alter user ID that's run in the script, special operation. So that's basically just to explain that piece of code. And I'm just going to show you a quick demo of what it looks like. So here, list user, we have 0 attributes, right? Next, we run elf.apf, which is the name of the script. We download it via FTP, Telnet, or whatever. And then we list all the APF libraries. So here, sys1.linklib, sys1.svclib, these are folders that we can write to, basically, because no rackf profile is defined. This is obviously just a test system, right? So all these folders are writable, and we can drop a program inside of them. So you can see here, we choose one arbitrarily. The script will compile the program. There was no error. And you can see that now we became special. It's as easy as that. Now, what I did was just weaponize something that obviously a lot of people were aware of. Like everybody from IBM to any auditor will tell you, hey, APF libraries, you need to protect them. But like I said, people are very stubborn, and proof of concept will get the fuck out. And that's the real attitude of people. That's how they assess risk. If there is no immediate or known threat, they will not address it. So what I did was basically just weaponize it and makes it like easy for any pen tester who's facing a mainframe to download the script, put it on the mainframe, and boom, they're root on the mainframe. So you do not have to go through the trouble of, all like digging into this stuff like I did just to know how to compile a freaking assembly code of 12 lines. So, like I said, a lot of people were aware of this, like APF library is very dangerous, you have to protect them, blah, 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 blah. And like Mark Wilson from RSM Partners discussed something similar, but using SVC. Now, SVC are supervisor calls, and just like on Linux or Windows, you have like, in Linux you have syscalls that go into kernel mode and, they do some fancy dangerous stuff and they bring you the result in user mode. Same thing on ZOS, but these are called supervisor calls. So these are just API functions that go into kernel mode, do something very deep, low level, and then come back. And now you have a table basically of 255 SVCs available. So from 0 to 200, these functions are IBM reserved, and 201 to 205 can be user defined. So like basically, Mark Wilson talked about some admins, some vendors that that register some SVC on the mainframe, some syscalls on the mainframe, that when they go into kernel mode, they make the whole program calling them go into kernel mode. Now this is very dangerous stuff, and I'm just going to show you what it might look like. So like they are dubbed magic SVCs. Again, I do not care much about the code. I'm just going to show it like there just to give you an example of what it looks like. What I want you to focus on is that there is not a single piece of authentication or access control in that code. Nothing. So, and by definition, everybody can call an SVC, right? That's what they're for. And so if you want to apply the same trick that we did earlier, you do not need APF libraries now. You just need this SVC that we say it's SVC number 233. You just call it in your assembly, and then boom, you can call the modset macro and go into kernel mode. So you do not need APF libraries anymore to achieve your privilege escalation. Now, I wrote this as a proof of concept to kind of learn more about SVC. So I wrote a script that will list all the SVCs in memory. Again, it's just a matter of walking from one control block to another. It's just one pointer to another. And it will basically check for some instructions that will, that are suspicious, that play with that piece of memory that controls whether we are in supervisor state or not. And so I focused on these two instructions. Obviously, this is not bulletproof, but it's just a proof of concept. So I focused on this first instruction that loads offset 540, which corresponds to the control block describing the current task that is running. And this second instruction that flips a certain byte at an offset 236 in memory. So I just decided to write a small regex like in Python, rex, not Python, to find all the SVCs in memory and check whether or not they perform these fishy operations. And I'm just going to show you what the script looks like. So here we execute elf.svc, and you can see that we type in list, and you can list all the SVCs that are running. And you can see that, and it inspects the code looking for an off bit. So SVC 233, off bit was detected, and it dumps the upcode of the SVC. And you can see here that we have no attributes. And when we rerun the program and specify this time the SVC, it will again compile the program, drop it into any folder. We do not need APF libraries anymore, and it will go into kernel mode and patch that ACE bit and make us special. So that's what it did here. Now, when I first coded this, I just wanted to keep it for myself. I was like, who's gonna, use it in the wild? I mean, have a magic SVC, magic syscall that lets anybody go into kernel mode? Like, who's gonna do that? And then I was talking with Soldier of Fortran, and we were talking about these privilege escalation possibilities, techniques, etc. And then, at some point, we talked about elf.svc, so this script that I showed you, and he exactly said, dude, I need to show you something. And he showed me this script that basically there was a mainframe breach in Sweden in 2012. And he was involved in investigation, so he got access to some scripts, involved in a good way, not in a bad way, by the way. Anyway, so he sent me this script it's on his GitHub anyway. And you can see here that this is a script that the attacker used. Now, I think you will now be a bit familiar with some of these instructions. So you can see that the attacker basically called an SVC 242, called the modset macro, exactly like we did, and then flipped some bytes in memory that are related to the ACE flag, ACE special operations, etc. It's exactly what I just showed you. So this, just to say again that this is real stuff that works in the wild, and I was very surprised to actually know about this script, and I was, wow, holy crap. Anyway, and this further, proves my point of the difference between the security maturity in the Windows world or Linux world and the mainframe world. People in the mainframe world still think they can get away with security by obscurity. A lot of people think they can get away with it. Well, we know it's not true, obviously. Every time there's this awesome code that says every time you think nobody will go through the trouble of doing something, some kid in Finland goes through the trouble. Well, this is basically the same thing. Now, kidding aside, like when you think about the logic of how these scripts that I wrote operate, they go into kernel mode, they become special, and then they alter the RACF table to make the user who called them special. It was not very OPSEC proof. I did not like it that much because we write something into the RACF table. I did not like altering the RACF database. And second, in the field, you can be special all you want. Doesn't mean you can access anything. It means you can give yourself access to anything, to something. And figuring out which resource you need to access to in order to, get business files and all that stuff is hard on a mainframe. Like doing stuff on RACF, manipulating RACF is very hardcore stuff. Like some companies have a dedicated RACF administrator to do this stuff, and you come in as a pen tester and try to mess up the rules to access this business app, it's hell. So it kind of troubled me a lot because I wanted to get some business data. I wanted, to really get something out of the mainframe, not just show that it can be root. So I decided to write a program that does what basically Incognito on Windows does. Incognito on Windows steals the token descriptor so you can impersonate other users. So same thing on ZOS. I decided to do the same thing. And like I said, the token descriptor, the equivalent of the token descriptor is the ACE. So the idea is to write a program that will dive into a foreign virtual address space, foreign user, grab the ACE, the token descriptor, and then copy it over into our own session. So the ACE, again, is 168 bytes or so of data. So you have user ID, group names, user flag, privileges, terminal information like pointers, etc. And the idea is to copy these fields from a foreign virtual address space. Now, obviously, not so easy because, like I said, each user and each program runs in their own virtual address space. So you cannot just dive into any a foreign virtual address space like that. And in Windows, I'm not going to say it's easy, but it's practical. You have APIs to do it. You have, write process memory, read process memory, open process memory. On ZOS, you have zip, zero, nada. You have assembly instructions if you're that brave. And so basically I decided to write, a script that will do all this stuff. So, you can easily do some proof of concepts and use it in your pen testing engagement. So, just like on Windows and Linux, you have some address space that are shared, some are private, etc., etc. And the ACE is located exactly here. So between the 8K and 24K, so in the user region area. And like I said, the idea is to run a program that will go into kernel mode, issue some special instructions that go into cross-memory mode, copy the ACE using some special instructions, bring them back in this primary virtual address space, then go into kernel mode again, dive in, cross-memory operations, pass the ACE that we just got earlier. So this is what basically the script does in its essence. And this is just a small demo. Again, it's on GitHub. It's called elf.self. And you can see here that list user, my user is special right here. But if I want to access the file that's called ibmuser.test, which is owned by IBM user, you can see here that security verification failed. I do not have the right. Now, I can add a RACF rule to allow access, but I do not want to touch the RACF rules, okay? So what I do is basically I execute my script with the list operands, and you can see here that these are all the programs that are running and all the users that are currently connected. You can see here that IBM user is connected. So we can relaunch the tool and this time set IBM user as target and specify an APF library that we can write to or SVC that is vulnerable, and then we become a IBM user, as you can see here. And once we are IBM user, now we can access the file, and we did not touch the RACF database. That's the beauty of the script. And here I'm going to launch the GUI so we can actually see the contents of the file, but it's basically the same operation as before. So view file, and you can see here that, hey, we have access to the file. So in summary, basically, if you have to get some key points out of this talk, it's just, A, mainframes are not legacy. It's a lie to say that mainframes are legacy. They power the world economy. For God's sake, 87% of credit card transactions run through mainframes. So we should care about them. As pen testers, as security researchers, as clients, whatever, we should look into this stuff. And it's really the Wild West because, like I said, many concepts, many security by obscurity stuff. So it's really the Wild West, and we can have some really great fun. And yeah, now there are tools to pen test mainframes, so check them out. If you want to contribute, please, we can talk afterwards about how to set up the platform and how to get access to it and how to write tools to do it. Thank these awesome people that I work with on the in the mainframe world. And yeah, if you have questions, please do not hesitate to ask afterwards. This basically concludes my presentation. Thank you very much.